Alright, so let's have a look at this here. So we can see that our little initial start here, we have two people. We have Alice and Bob here. Alice is standing here at the corner of 1st Avenue and East 3rd, and Bob is standing at the corner of 2nd Avenue and East 5th. For the simplicity of this problem here, for the sake of this problem, let's assume that all the blocks are square and they're just one unit here. That just makes things a little easier. So in our first situation, Alice wants to walk to Bob's location. What's the length of the shortest path that you walk? Now, for those of you who have been in the city before, you'll note that it's pretty easy to see that there's only that you have to travel 3 blocks here, right? So in this situation, for instance, one thing you can do is you can go up like this, go up on 1st Avenue to 3rd Street, to 5th Street, that's 2 blocks, and then go one over to 2nd Avenue, that's a total of 3 blocks here. Alternately, you can do you can reverse it here and go like this, go along East 3rd Street like this until you get to 2nd Avenue, that's 1 block, and then go 2 blocks up north on 2nd Avenue. Or you can just sort of do the same thing, a little bit different here. You can go up 1, make a left, go along East 4th, go to 2nd Avenue, go up 1 again. So you get 3 blocks here. So it's pretty clear that in this situation, this is going to be 3 blocks here, right? Now, the nice part about this 3 blocks thing here, ladies and gentlemen, is that this actually, if you look in the mathematical literature, this is actually known as the taxicab distance here, because if you were to take a cab in the city or an Uber to get from here, A to B, you would have to travel 3 blocks here, because you can't travel through the blocks here. This taxicab distance is often used in a lot of tactical role-playing games, whether it's on the, over the table, or in video games like Advance Wars or Fire Emblem, things like that. You use this sort of thing here. Now, in problem 2, a baleful polymorph turns Alice into a crow. Don't you hate it when that happens to you? So, in this situation now that she's a crow, she's no longer bound by the restriction of walking along the blocks here. So that means what she can do is just simply take this distance like so. She can now fly directly there. Now, it's pretty clear to see that in this situation, we can create a triangle like this here. If we put, a point C here, we can see that we can create a triangle like this one here, and therefore we can see this is 2 and this is 1. So, let's make the assumption here that the streets are always perpendicular to the avenues here, like they should be in New York. So then we can just simply use the Pythagorean Theorem here. We know that's going to be 2 squared plus 1 squared is going to be our distance squared. So D in this case is radical 5. So we can see that in this situation now, we're radical 5 blocks here. We've actually changed it up slightly, made it a little bit different here. Okay? Now, note that in this situation here, right, what we looked at this 2 and 1 here. If we think about Alice's situation, she's at the point 1, 3, and Bob, we can think of this as a 2, 5 here. Now, note that this 2 here, really, if you think about it, it's just a difference between the avenues. So it's really 2 minus 1 here. And this, oh, I'm sorry, I screwed this up. This should be 1, this should be 2, my apologies. And this 2 here should really be 5 minus 3 here. So we have this sort of thing like so. And we can see that in this situation here, we have the 5 minus 3, we have the 2 minus 1 here, and that gives us an idea of that maybe that there's something else going on here. So if we look in the Cartesian plane, if we look at the coordinate plane here, right? If we pick 2 points here, A and B, and this time we're just going to give them arbitrary points here. So I'm going to call this A, x1, y1, and 2B is going to be x2, y2 here. We like to calculate this distance yet again between the 2 points. Oh, there we go. So note that just like we did in our picture up here, we created a right triangle. We can do the same thing here. And creating the right triangle is pretty easy here. We're just basically going to try to create ourselves 2 sides here. The legs are going to be parallel to the axis. So we want a horizontal axis like this, out like so. And we can create a vertical like this here. And they're going to intersect at this point here, C. And we know there's going to be a right angle. Now, based on what's going on here, it shouldn't be too hard to show what point C is here. Note that it's going to be at the same the y coordinate, so there's going to be y1. And here, by being on a vertical line here, there's going to be the same x coordinate, so it's going to be x2 here. So much like we did over here with the difference of the coordinates, we can do the difference of the coordinates here as well. So therefore, this is going to be x2 minus x1, and this is going to be y2 minus y1 here. So, according to our Pythagorean theorem, we can now put everything together here. So our Pythagorean theorem tells us here that x2 minus x1 all squared plus y2 minus y1 all squared should be equal to d squared. This is just Pythagorean theorem here. Now, do note that that's d squared. We want to solve for d, so we can very easily just take the square root of everything here. So we take the square root of all sides here, d squared just becomes a d, and then we have this rather nice looking thing here. And we have x2 minus x1 squared plus y2 minus y1 squared is equal to d. And that is going to be our vaunted distance formula here. And in fact, that's actually going to be really helpful. The distance between 2 points located at x1, y1, x2, y2 is this here. Now note that all I did was that this is derived directly from the Pythagorean theorem. This is coming from the fact that d squared is equal to, in this case, y2 minus y1 squared plus x2 minus x1 all squared here, right? This is just the Pythagorean theorem. Now, if you remember when we talked about the Pythagorean theorem in class in the past, you remember that the Pythagorean theorem actually also works in higher dimensions as well. We can actually stick extra things onto it, right? In fact, you may recall in one of the lessons that we did earlier that we had the Pythagorean theorem work in 3 dimensions. So because the Pythagorean theorem works in 3 dimensions, we can create a distance formula that works in 3 dimensions as well. So we want to go into, because we know that in 3D here, we know that d squared equals a squared plus b squared plus c squared here. We can do much the same. We can do the same setup here, and have the fact that now we can have, again, our y2 minus y1 squared, our x2 minus x1 all squared, and now we can stick an additional thing on. We can say a z2 minus z1 squared, right? And that's going to be the distance in the z-axis here, and that's all going to be equal to d squared here. So therefore, d, we can create a version of the distance formula in 3 dimensions here. So I'm going to create it sort of in alphabetical order here, right? So we can do x2 minus x1 all squared plus y2 minus y1 all squared plus z2 minus z1 all squared here, right? So we can see that there's a version of the distance formula that actually works in 3D here. And you can actually extend this to higher dimensions. So you can have a straight line distance between 2 points in 4 space here, and 5 dimensions, 6 dimensions, and so on here. And all of them will work out in much the same way here.